I'm sure that everybody in this room knew Bill, and personally, for reading his work, was as sad as I was when we received the news in January. And many here will have had the same thought that something needs to be done at this meeting about honoring Bill. And I'm very grateful that the organizers were extremely receptive to this and organized and provided for this session. Of course, I feel extremely honored to chair this session. I think there are lots of better choices, but okay. I was in contact with Fatima, his wife, and she sent me greetings and best wishes for this session. So let me read this to you. The Lawvere family wishes to convey our warmest greetings and heartfelt best wishes for the impressive Category Theory 2023 conference. We are deeply moved that you have decided to hold a special session in Bill's honor. It is astounding and gratifying to see the work which Bill participated in find so many interesting expressions in the wide variety of topics, and the many veteran and up-and-coming researchers who continue to push the limits while also bringing the wider mathematical community together through the unifying and simplifying spirit of categories. I asked Danilo to look for photographs, and he sent me in particular this photograph with the caption reading "My dad" in 1977 in the campus newspaper The Reporter. The article was announcing the Martin Chair. This allowed for the categories in continuum physics meeting in 1981 in Buffalo, and the publication based on the conference. So I'm very pleased that we have now a wonderful list of speakers and contributors that will be led by Kock, who will have a half-hour presentation and followed by shorter communications, 10 minutes each, by Peter Johnstone from Moerdijk, Matias, Menni, Rosolini, and Janelidze. Please understand, we couldn't have more speakers because of time constraints, but I'm sure that there are many memories and anecdotes and contributions that would be worth having here, that have to be relegated to the hallways, I'm afraid. I have to ask the speakers to please keep the timeline. In fact, it would be good if you stayed slightly below, so we have a little bit of time to make the technical changeover. And if you're more generous to the audience, then there could be questions. Otherwise, there wouldn't be any questions or comments. All right. So now, without further ado, Hannes, please come forward. So you take
I'm very happy to be here for this. This is another photo by of Bill. I would like to start thanking the organizers and also thanking Maria Manuel Clementino and Jorge Ricardo for providing this picture, which is part of the very informative interview which they conducted with Bill in, was it 1907 or something? There'll be a URL for it at the end of the talk. Also, I would like to thank Fatima and Danilo, who has for the friendship and for providing me with much information and other things that my presentation is based on. So this is, you can see a little bit what I had just said. But let me go to the issue. And the issue starts this presentation starts, there was a meeting, a CT meeting in 1987 here in Lorraine. Although one afternoon was transferred to Leuven, then this was at a time where the controversies between the Flemish and the French-speaking was not completely gone. And so I think Lawvere wanted to put something about that, which the key word is unity. And also from one of the textbooks that he wrote together with Steve Shanwell, that's an undergraduate textbook in fact. They say the unification of mathematics is an important strategy for learning, developing and using mathematics. Lawvere was very interested in that things should be so simple, the concepts should be so simple that they could be explained to non-mathematicians. And there were several non-mathematicians participating in the development of this textbook, like this one, and also the other one with Bob Rosebrook, Sets for Mathematics. Now I want to start a little with some historical remarks about the development of category theory. In fact, this textbook writes well about the predecessors like Dedekind and Cantor and many others who, before Heidenberg and MacLean came into the picture. But one could say that the notion of category and function that was invented by Heidenberg and MacLean in order as a tool in algebraic topology, namely in particular functors that go from the category of topological spaces to the category of chain complexes or abelian groups or something like that, homology functors and cohomology functors. And later on came another important step, namely seeing the simplicial sets, which have been used a lot, that this suddenly was seen as a functor category from the category delta, as it's called nowadays, controller functors from delta to sets. I think that was one of the achievements of Daniel Kahn, who also introduced the crucial notion of adjoint function, which is really what category theory as such, as we know now, starts. So at that time, categories and functors were used in wider and wider contexts. But the crucial and radical step was Lawvere's seeing that this was not just a unifying tool, but that it really was, that this unification method was the foundation of mathematics. And in the La Jolla proceedings from our category theory conference, well, it wasn't called that in 1965, but he had the article with the title "The Category of Categories as a Foundation for Mathematics." But then he says that that the tradition of foundation as a justification, building all the way down to the empty set and the other iterative constructions of epsilon-based set theory, that had not helped mathematics very much. And he uses foundation in the sense of, for instance, Eisenberg Steenwald's foundations of algebraic topology, and likewise mechanical foundations of elasticity and fluid mechanics, published same year by Truesdell. Truesdell was Lawvere's first mathematics teacher in Indiana, and his subject was continuum mechanics, which was also Bill's main entrance into mathematics. And he saw that to have a reasonable, rational theory of continuum mechanics, one needs a category of good spaces. And he reasoned that Brodnick's theory of a billion categories, AB5 categories, should have a non-linear analog whose examples would include categories of sheaves or sets, and noted that on the basis of my work on categories of the category of sets, such a theory would have greater autonomy than the abelian one could have. This is, of course, in some sense, the beginning of the theory of elementary toposes. This shift from categories and functors as a tool relating this and that showed that this is really the foundation of mathematics. Can be seen also in one of the category theory founders, maybe MacLean, who has two important textbooks. The one, Homology from 1963, and the very useful categories for the working mathematician in 1971. And the latter title sort of indicates that now it's not just a tool for algebraic topology and homological algebra, but for every working mathematician. And MacLean puts as one of the slogans in the book, adjoint functors arise everywhere. Well, that's a rather short span in these years, but I think that was a crucial time for the development of category theory. I could say in the textbook Homology, the word adjoint functor appears in a note in small font as a remark. Otherwise, it doesn't appear in the book. And in 1971, adjoint functors arise everywhere. That sort of illustrates the... Personally, I experienced this change when I was in Zurich, where Benno Ekman had organized I think 1 year long special year of category theory. Well, it wasn't really called that. The proceedings, I apologize for the poor scanning, but it's called Seminar on Triples and Categorical Homology Theory. Triples we know nowadays called monads, of course, but still it wasn't on category theory, but on categorical homology theory. They were using at that time, as they do nowadays, triples can be used for constructing simplicial objects. I came as a PhD student to Zurich when in 1966, and Bill was very kind and shared his office with me, and I learned a lot of things, and Bill told me many things that I don't understand, but he was full of ideas when the afternoons when we sat in the office. He also took me to Café Odeon in Zurich, where this picture is taken in the fall of 1966, and he explained me that Café Odeon was also the place which was visited by Lenin when he was in exile in Switzerland, and also by Einstein. So I felt I was in a nice place. Now I will give a short CV of the years after Zurich and until Bill settled in Buffalo. You can see them there. 69, Bill was chairing a group of category theorists, and prestigious appointment to the Dalhousie University. This was, and I joined him in Halifax for the first year, but the contract was not renewed due to Lawvere's political activities. He was protesting against some fascist measures that the Canadian government was trying to impose on the protests. So he had to leave Halifax, or couldn't have his contract renewed. So in 71 to 72, he had a position in Aarhus, where I also worked together with him. 72 in Perugia in Italy, and from 73 on he was in Buffalo, except for several visits of shorter or longer nature. I think it was 1 year in IHES in Paris. In 67, he gave some talks on categorical dynamics, which have turned out to have many fruitful ramifications. But roughly speaking, since he now was in the position of the notion of Cartesian closed category and exponent objects, he realized that why not think of a tangent bundle of a manifold as m to the d for some postulated infinitesimal object d. And later in the 1970s, an aspect of this theory was developed as synthetic differential geometry, where one further postulates a commutative ring R, which we think of as a geometric line, and require that the tangent bundle of the line should be R cross R, R to the D and R to the R should be isomorphic. And out of that simple axiom one can start developing a lot of geometry, or kinematics if you want. This is still far from being a fulfillment of the project of categorical dynamics, which is still ongoing, and it's really something that one should. Now I go back to some more personal. This is not from the year when he was for a year in Aarhus, but he came many times during the summer, and we were good friends all the time, and we were often together. Here is Fatima, who was this nice letter, and Bill and me and my wife, who's also here in Geneva today. Also, there was also a short message from Danilo, which is Lawvere's son. That's a tall guy behind. I should say that the picture is taken on the top of the Mathematics Institute in Aarhus, where we had very nice apartments for our visitors, and the Lawvere family was staying in one of these apartments, and it's on the balcony of that apartment where this photo is taken. There are two, there's also my daughter and Lawvere's daughter, and then the other guy is Joachim, who will give a talk on Thursday, I think. Is it Thursday, Joachim?
Friday.
Friday, okay. In Aarhus we had 3 conferences with mainly category theory, for instance 73 and then 78 and 83, and among the things that took place at the open house in 78 were some discussions on philosophy, a session with discussion of philosophy with Joel and Lawvere, and some of the contributions there are also published in, as you can see towards the description, in the smooth topos of the dynamically possible motions and deformations of a continuous body. So still, the aim was this continuum mechanics. And now I go to some aspects. This is also from this article in Cahiers de Théologie Géométrique Differentielle Théorique from 1980. The scientific world picture has on the one hand matter that moves. That's the world picture. But inside matter, you have the brain, which thinks, and that's the circle. And because it thinks, it has also then a picture of the matter that moves, which then sits inside the thought. That's matter that thinks. That's the small square, a reflection of the. There's also a mathematical world picture, and where Lawvere says mathematics is the study of space and quantity and their mutual relationship. The logic of mathematics is not directly studying space and quantity, which are external objective things, but are the concepts, constructing concepts for thinking about these things. And he says, I agree with Brouwer that n, the natural number object, is subjective in contrast to the continuum, which is objective. So in the circle here we could ask the concept of the continuum, but it has different status as the concept of natural numbers. The object of natural numbers you don't find in the world. That is in the brain, that's a thought, a useful thought, but it doesn't exist in the same way as the continuum does. The continuum is a concept that is derived directly from our historical scientific experience with the world of matter and motion. It's not only a mental form construction, n and o. It's not just like n and omega, the subjective idealizations of iteration and truth respectively. These two mental constructions are crucial in much of topos theory, although we know that we can do without the natural numbers in some context. Yeah, you know all that about how we construct the real numbers, a model of the continuum out of n and omega in the topos. But n is subjective and leads to some things like space-filling curves, which of course does not exist in the world. That has nothing to do with the real world. And now I shall use a few minutes to talk about the relationship between space and quantity. And this is from my notes from the talk, one of the philosophical discussions in 1978 at the open house at Aarhus. You have a very rough picture, which has to be elaborated as mathematics, but but you have a category of spaces, and that should probably be a topos, a category of spaces. And then you have a category Q on the right-hand side, which should be the category of physical quantities, or as we would say nowadays, dimensions of physical quantities, among which you have length, area, volume, mass, time, span. So these are all physical dimensions, not to be confused with the pure quantity, which is also among spaces. In fact, the spaces, well, that Q, the physical quantities or physical dimensions, form in a Picard monoidal closed category, meaning that the unit object, if you dualize it to a unit object, you call it the object, dual of an object B, you call it B star, and the canonical map from B star tensor V back to R, the unit object, has to be an isomorphism. That's the characteristic feature of, like the category of one-dimensional line models over topological space. And there are passages between these two sides, and well, yeah, that's what I said if you didn't listen. This relation between space and quantity is leads to progress. That's two different things, and you have to be aware of the distinctions and passages from them. For instance, you have the former side on the right, and which is on deduction, and the conceptual side on the left, how you can, by introducing a coordinate system, find the solution to the equation. The logic of mathematics is that part of mathematics which does not immediately relate to the real world, but to the concepts that you have developed. And that the two aspects of the logic, namely logic of conceptual construction, that of constructing the concepts that will guide us to conclusions, and then there's the logic of formal deduction, which is calculation, so to speak. And every many progress in mathematics depends on having this interplay between the concepts and the deductions, the formal deductions. But Lawvere says that you should not think that deductions is everything. It's not the whole thing, and sometimes there are people who wave the fact that only what you can deduce has value, that they oppose the idea of the conceptual construction, and thereby oppose the purpose of mathematics, which is clarifying and guiding, which the concepts do in a different way than the formal deductions and calculations do. And one of the ways he formulates this is to say that the existence of Euclidean geometry is more important than any specific theorem in it, and that the fact there must be a continuum is more important than the way you construct it. Euclidean geometry was, from the outset, based on the concepts plane, line, and point, which derived from experience with the world, the physical world, say architecture. Line is a concept derived from the physical notion of a taut string. That's typically made of linen, and I have been told that the word line and linear and all that comes from this word for a string made of linen. Now I want to finish in 3 minutes. I will mention 3 persons, or really 4, that play a role. First, Rosolini, who of course strongly influenced Lawvere's work. And Rosolini was actually in Buffalo and gave a series of talks in the spring of 1973, while Lawvere was still in Perugia. So Lawvere did not attend this colloquial talks. And according to Michael Wright, who is also here, none of Rosolini's talks to the Buffalo Math Colloquium were recorded, and Bill attended the great notes only on the last talk. Bill gave an account of the talk in the course of a discussion held at Mike Wright's place in Foucher in 2005, and now finally in the course of being described. I hope things are going well with that, Mike.
Yes, I hope to report progress soon.
Rosolini saw narrow sense logic as fitting within broad-sized geometry, what Bill referred to in passing as Rosolini's version of how to bypass logic, which you may put in a very primitive way, that good concepts imply that you need fewer proofs. Another person I need to mention is Steve Shanwell, who was in Buffalo and was Bill's daily collaborator for decades, privately, and that's the type of orders. It's Steve Shanwell with white beard. Yeah, there are some anecdotes here. The blue thing is again a quotation from Bill, and Daniel say that Fatima made sure that, well, she functioned as a secretary and also as a producer. She was the one who insisted in having these 2 undergraduate textbooks produced. Okay, now I finished by, that's the question of Nachlass. All the things that Bill has left us with, notes from talks and unpublished manuscripts and recordings made by, for instance, Michael Wright, and the papers that Daniel was taking care of in Buffalo. He says that he will use now years to organize this Nachlass, and on the website, the old website of the years. And I have also some scannings of many of the lectures of Lawvere that I have attended, and they can be found on my homepage, which is written there, and you add then the date and .pdf. For instance, the one with the square and the rectangle is the date, the 5th of May, the 24th of May. Thank you.
Thank you very much, Jonas. You brought a big part of Bill alive again. Felt like Bill's lecture. Thank you.
So I haven't got any slides to show you. I have written out a talk, which I wrote out to make sure it lasts 10 minutes. And what I want to do primarily is to say a bit about what I think most of us would consider Bill's single most important contribution to mathematics, which is the creation of the development of the notion of elementary topos. I will say a few personal reminiscences later on, but that's the main thing I want to talk about, how the notion of elementary topos came into being. Now, the statement that it is Bill's most important single contribution does require a qualification in 2 directions. Firstly, of course, it wasn't Bill's single-handed achievement. The details were worked out during his collaboration with Miles Tierney at Dalhousie in 1969 to 70, And Miles, who probably had more familiarity than Bill with the work at the Rosolini School in algebraic geometry, was certainly an important part of that collaboration. But I'm pretty sure it was Bill who actually laid the foundation by finding the right axioms. And I will give justification for that. First of all, he had, from the time of his PhD thesis, been working on the idea that an elementary axiomatization of categories of sets would be something that would enable one to do set-theoretic mathematics inside them. And it seems to be quite early on, possibly as early as 1966, that he realized that a sufficiently flexible axiomatization to be useful ought to include the categories of sheaves that were studied by the Rosolini School, as well as more narrowly set-like categories. In fact, Bill had first learned about the Rosolini School work from Janelidze during the 1965 La Haya conference, which Anne has mentioned. He expressed his need for flexibility by a simple analogy. Fields are mathematically interesting objects in their own right, but we learn a lot more about them by studying them in the context of the larger category of rings. Another slogan of which he was fond was that the basic contradictions in mathematics should all be expressible in terms of adjunctions. And it was his search for an adjunction theoretic formulation of the set theoretic schema's comprehension that led him to the notion of subobject classifier, which was the absolutely key notion. As far as I know, he first presented these ideas publicly at two conferences in the spring of 1969, one at Rome in March and then at Oberwolfach in May. Significantly, the second of those was a workshop on the continuum problem, at which he argued that the correct way to interpret Cohen's forcing method was in terms of sheaves on complete Boolean algebras. And it cleared from the abstract, which he wrote for that talk in May 1969, which is available online, I've got a copy of it here, that he already had the notion of subobject classifier as one of the key elements in an elementary axiomatization of what toposes should be. And of course, he'd already identified Cartesian closeness as the key thing in his thesis, although he wasn't responsible for that name. So Bill had the basic ingredients of the definition by May 1969, but of course, a lot of work was needed, first to show that those ingredients were sufficient to imply all the exactness properties of a Rosolini topos, and then to show that constructions such as three-sheaf categories and sheafification could be developed in that first-order setting. And that work was done jointly by Bill and Miles in the area of collaboration, and it was first presented to the categorical community in 4 lectures, 2 each by Miles and Bill, at the August 1970 meeting of the Midwest Category Seminar, which took place in Zurich, and then to the wider mathematical world in Bill's invited lecture at the ICN in Nice the following month. Now, because Miles had, before that collaboration started, Miles had been thinking about the need for an elementary development of topos theory, but I don't think he'd ever got near the idea of subobject classifier. That was undoubtedly Bill's achievement. So the other potential qualification to the claim that Bill was the sole begetter of topos theory is that one has to ask, how much did the Rosolini School actually know about the elementary axioms? Of course, they certainly knew that toposes were Cartesian closed. Giro's axiomatization includes the requirement that all arbitrary colimits should be stable under pullback, and given the other axioms they had, that ensured that pullback functions had right adjoint, in other words, that the category was locally Cartesian closed, and indeed, exponentials appear explicitly in section 10 of expose 4 of SGA4, and they prove a number of results exploiting the Cartesian closed structure. For example, the fact that the adjunction induced by geometric morphism is automatically enriched over the codomain topos. So they knew all about that, but they chose not to include it in the axiomatization. They were totally uninterested in freeing their work from set theoretic conditions. I suspect that was the result of their Bourbakiste heritage. So it was universality of colimit rather than local Cartesian closeness that appeared in Giro's axiomatization. Now, regarding the notion of subobject classifier, there's a sort of persistent rumour that I've heard many times that was actually defined somewhere in SGA4, just as an example of a sheaf on an arbitrary site. And I've even seen it said that Bill and Miles chose the letter capital omega to denote it because that was what it was called in SGA4. As far as I can tell, that's simply not true. It's certainly not in the published version of SGA4 that appeared in Ring lecture notes in the 1970s. It might conceivably have been hidden somewhere in the mimeographed version that existed in the 1960s, but I've looked for it and I haven't managed to find it. And if it was there, why did they take it out of the published version? And also there's clear evidence that Rosolini himself acknowledged that his failure to think of that concept of subobject classifier was one of the major failings of his and his colleagues' work in toposes. By the way, in the 1969 Wolfram abstract to which I referred, Bill used a curly figure 2 for the subobject classifier, and that could easily have evolved into an omega. So I think there is no doubt that that was something that Bill contributed and no one else did. Okay, so that's what I want to say about where the axioms of topos theory came from. For the rest of this tribute, I'd like to strike a more personal note. So I first learned about elementary toposes from Miles Tierney's lectures at the 1971 summer school in Verona in Italy. I didn't start working in the field until the autumn of '72, when Saunders MacLean spent a sabbatical term in Cambridge. And Saunders mentioned in his lectures that there was an open problem to give an internal version of Grothendieck's iterated colimit construction of the associated chief functor, which could be used in the elementary context. Now, I'd already learned a bit about internal categories and colimits from Tierney's lectures, so I thought this is a problem I might actually be able to tackle. And by the end of the term, I'd actually solved it. So Saunders then strongly advised me to write it up and submit it for publication in JPAA, and suggested Bill as the appropriate editor to handle it. So I wrote up the paper and sent it off to Bill, who was then in Perugia in January '73. 6 weeks later, I received a quite remarkable letter from Bill, which I still have here. Bear in mind that at that point, Bill had no idea who I was. I suppose it's possible that Saunders might have written to him about this from a C1 student he'd met in Cambridge. But in that letter, he treated me, I won't say as an equal, because he recognised that I was ignorant of lots of things that he knew about the background of what I'd done, but as someone who'd be brought on to becoming a potential equal by the right sort of encouragement. And that's exactly what he gave me in that letter. 2 pages of insightful comments on the significance of what I'd done, which he urged me to incorporate in a revised version of the paper. I'm going to read an extract to you. The problem which you solved, namely to carry out an internal version of the Grothendieck-Chevalley-Heller-Rowe construction of this functor, as the associated chief functor, was presented by me at a conference held in Rome in March 1969, at which MacLean, Fry, Gray, Denaboo, Mitchell, James, Siegel, and others were present. I never wrote a paper for the proceedings of that conference because, 1, the framework presented was leading to the development of the elementary axioms for topos, and I didn't want to present that framework in a half-baked form, and 2, I, and later Tierney and I, were unable to solve the problem. The struggle with 2 led me in 1970 to give the opposite construction, which you, somewhat startlingly to me, refer as the old construction. Thus, it was precisely the need to have objects like what you call, which you denote by p hat, that's the internal presheaves, which was one of the main reasons for the existence of the theory of elementary toposes. And further, it has also been true in this context, as usual, that a spiral development was historically necessary. And at that point, he drew a diagram in the letter of the spiral he was referring to. As you can see, the information content of that letter was pretty dense. I confess that I struggled to understand it at the time, but I realised straight away the enormous favour he was doing me by writing in such detail. And that set the tone for all my subsequent correspondence with Bill. His letters and his published papers were always so densely packed with ideas. It took a large number of rereadings to assimilate them all. A prime example, which I think Matias is going to talk about, was his 2007 paper on axiomatic cohesion. That paper is a real goldmine, and they're still extracting nuggets from it 15 years later. I did, of course, rewrite my paper, doing my best to incorporate Bill's ideas, and it was duly published. A few months later, in May 1973, I met Bill for the first time at the Authors' Open House, which Alice has already mentioned, the first of them, and I discovered his lectures, though they tended to start slowly, could also be pretty densely packed with information. They also tended to go on a long time. One of the delightful things about Bill, really, was that once he got started on the topic, he just lost all concept of the passage of time. So his lectures could go on for an hour and a half, 2 hours, and people sat through them. Interestingly, the topics selected in Aurus at that time were not primarily his own work. It was the theory of classifying toposes, which had just been introduced a few months earlier by Gonzalo Reyes and his student Jean Dion. So Bill was presenting that material, since Reyes wasn't there in Aurus, for the benefit of the mathematical community, although he did add a few ideas of his own to Gonzalo's work. So that first meeting in Aurus, I mean, in one way it wasn't an entirely happy one for me. As Alice will remember, I attempted towards the end of the meeting to give a rather light-hearted talk on a non-categorical topic, which was viewed by Bill as an affront to his strict Marxist view of what mathematics should be about. We did have a rather public row about it, but it didn't prevent us becoming friends. And that was the great thing about Bill. He was capable of disagreeing passionately with someone about politics or religion, while still valuing their scientific contributions. And I'm glad to say that Bill and I remain friends for almost 50 years. Thank you.
We're running over time. Ieke is next.
I would like to take this opportunity to illustrate what an enormous intellectual jump Bill's contributions made for me. And to explain this, I should say that I did my PhD at the University of Amsterdam in the period 82-85. And is there a piece of chalk somewhere? So before that, as an undergraduate, I learned about intuitionistic logic, intuitionistic arithmetic, intuitionistic analysis, and how to deal with the Dedekind reals and the Cauchy reals and how they could be different and all that sort of thing. And I learned how to manipulate these things. That was all sort of the heritage of Brouwer in Amsterdam. And we were concerned also with models of these axiomatization of intuitionistic arithmetic and analysis. And we learned about cryptic models and the dialectical interpretation and realizability models. And then in 82, 83, Gonzalo Reyes, who Peter just mentioned, spent a sabbatical in Holland. And I started to learn about topos theory and about elementary toposes. And I think this was also a line in one of others' slides. Pretend it's just a category of sets. But you have to use intuitionistic logic. And this was very easy for me because I was very well trained in doing this. So it was a great eye-opener for me. And also just the idea of doing mathematics in such a universe instead of just trying to show that a single action does not imply another one and looking for specific independence proofs was a completely different point of view. And I think this also had a great payoff in the theory of grounded toposes. I think it is wrong to contrast grounded toposes and elementary ones. Every grounded topos is an elementary topos, of course, but I think the idea of viewing a grounded topos as an elementary topos as a universe of sets, where you can use the power set, where you have your subobject classifier and do mathematics inside it, means that if you have a map of toposes F to E, you can view E as your universe, and if F and E are grounded toposes, I should say, and just study F from the universe E. Okay, and this was in the early 80s a very profitable technique. For example, we heard articles about the work of Joyan and Tierney about the representations of toposes by groupoids. It's all based on this idea of handling, for example, these enumerations that we heard several lectures about dealing with them intuitionistically inside the topos, which in this case is E. So this entire development that we hear about at this conference 40 years later would not have been possible without Bill continuously emphasizing this point of view. Another thing that has been mentioned and that had a great influence on me in the same period when I was writing my thesis was that I was working with Rosolini for models of synthetic differential geometry, and I remember and found several correspondences about how enormously encouraging Lawvere was in those days. He was always very positive and encouraging, and had a great influence on me. He was also, I spent the year 84, 85 at McGill. Tony was there at the time, and Lawvere came, and I visited Buffalo in those days. He also came to Holland. I haven't tried to exactly find the year, but now that I think about it, my wife was working on probability in those days, and he was immediately trying to encourage her to write a thesis on category theory and having a completely different approach to probability. That never happened, but it's entirely typical of Bill to make such remarks. And maybe this has now been materialized in the talk by Ruben van Bellen. I'm not sure where he's sitting, but he was there, using category theory for martingales and measure theory. There are two things that Bill asked me to think about, which I maybe didn't quite fulfill. One is that he was very fond of Peter Johnstone's topological topos. And so he urged me to study this topos, and I found some correspondences where I claim to have found the Quiller model structure on the topological topos, so I'm carrying sheaves, not simplicial sheaves. Well, I couldn't find any notes of the proof, but in hindsight, it was probably what is now a standard transfer of model structures, but this was, of course, before the notion of transfer existed, before cofinitely generated model categories existed, so it was it's quite a long time ago. And the other thing that Bill was quite obsessed about and wanted me to think about, well, I never got very far with that, was the distinction between gros and petit topos. And I think we will perhaps hear more about this from Matias Menni. But all in all, I remember Bill as an extremely positive character, always encouraging, always open-minded, always prepared to drag people into the camp of category theorists, and being a real leader and inspirator there. So thank you.
Thank you for the lively presentation. Matias, please.
When we remember someone, we don't just recall their greatest achievements. We also reflect on other things. A kind gesture, a small display of courage, and maybe an insightful remark. Because of that, I'd like to go through some of Bill's 1990 thoughts on the future of category theory, concentrating on the ideas that had less impact in our community. He suggests in the introduction that he's motivated by the search for a more accurate conception of space, and outlines a positive mathematical program in 3 sections. The first one insists on the importance of clarifying the distinction between gros and petit that you just mentioned. The second section discusses the foundations of his dimension theory in terms of levels and their favor. He had touched these topics before by himself and also with other people, but it's here, I think, where their philosophical significance is more clearly exposed, together with new problems and conjectures. Anyway, the third section is different, I think. It involves at least three related ideas. Grothendieck-Stein topology, logicians working on the Tarski's problem of decidability, and also objective number theory. Citing a paper by Vandendries, Bill says that the rough similarity between Grothendieck-Stein spaces and the finitely subanalytic objects considered in logic is in fact a major difference. The same sort of difference exists between real algebraic geometry and semi-algebraic sets, as well as between the ordinary continuous PL category and the polyhedral category of negative sets. So he points our attention to three pairs of categories and stresses in passing that all of these are quite different from categories in which countable quadratic compositions are common. So none of these categories have the natural numbers object. The difference within each of the three pairs mentioned may all exemplify a single general process, which I will call Aristotelian intervention. This is a citation, okay? He writes this in the paper. So this is not in the paper. Let me try to draw it like this. Tame categories of spaces come in pairs. A continuous side and a discontinuous side. Tamely discontinuous side. And between them, there's this intervention. So let's look at an example. Let P0 be the category of bounded polyhedra and functions between them whose graphs are polyhedra. These are, as I insist, not necessarily continuous. They may have discontinuities, but only very, very few. It is an extensive category. And inside there lies the category of, the same objects but continuous functions between them. So is there a categorical way to get one from the other? Notice that on the continuous side, on the left, there's a good connected components counter, and it is also sufficiently cohesive in the sense that it has this connected object that has two disjoint points. On the other hand, the discontinuous side is Boolean, so nothing is connected there. And yet the Burnside rig of objects up to isomorphism has Euler characteristic and dimension. So there's a lot of geometric information there. Now, assuming one of these two items, what else do we need to build the other thing? Notice that, I know that Bill was thinking already at a topos version of this. Notice that the inclusion of PL into P0, induces a geometric morphism between the Gaeta topos. Is it determined by the domain or the codomain? We still don't know. Well, more generally, even a topos of spaces, let's say a precohesive topo, is there a geometric morphism towards it that deserves the name Aristotelian intervention? Bill told me that once that despite all the progress in categorical logic, there was little interaction between category theory and this branch of model theory that studies tamely discontinuous categories of spaces. So, I don't know why that is. It's a bit of a pity. Back to the sides, back to the level of sides. Bill also sketches in this section what was later called objective number theory. This, as you can imagine, this nonlinear variant of K-theory has many different facets. What's relevant to recall here is that if you have a polynomial with natural numbers coefficients, then you can build a generic solution to the equation x equals p to the x. This is an extensive category together with an object and an isomorphism, an object x and an isomorphism between x and px, which is the initial one. Why do they appear here? Because he was thinking that they could provide categories of thinly discontinuous spaces. For instance, the generic solution to x equals x plus 1 plus x has a canonical map towards P0, which sends x into the open interval 0, 1. Of course, he was aware of the difficulties, so he says that naturally models like polyhedra constructed from below, from real space, are more satisfying than those constructed from above by classifying abstract algebras. But as usual, the goal is to be approached by pushing hard from both sides. Oh, but he was, I mentioned Booleanness because I think it's relevant for this example, but he was ahead of that already. He comments in passing that certainly the resulting size used in this procedure need not be Boolean. For example, if you consider the half-open interval x, then it should satisfy that x equals 2x. But its endpoint will not be a coproduct summary. Yeah. This is the ancient Zapotec CT, near the place where Fatima and Bill and Steve Shannon used to work on the book of objective number theory. I'm sure you can find better pictures in the web, but you won't find this one. These Kiko ones took us there. Kiko and Moriko took us there. And, there they are, probably thinking about something that Bill said. How much time do I got? Okay, 45 seconds. Yeah, that's mainly, but I couldn't resist adding this. He says in the beginning of the paper, I think, that when Verdier described Topos theory on the beach, he was slow to grasp the significance of Topos theory. Yeah, he probably meant it. Yeah, that's it.
Thank you very much, Matias. Pino is next. The speaker is from Italy.
In fact, sto per parlare italiano. There will be little about the scientific inspirations and achievements of Bill Lawvere in the next 10 minutes. What I prepared is a few glimpses of the activities that a champion of category theory had come into a country for a year. Anna's mentioned from 1972 to 1973, Bill worked in Perugia on a community of mathematicians that probably didn't know the luck they were going to have. He was called on a chair in algebra at the University of Perugia, and during the year he spent there, he had the possibilities of traveling around Italy to several universities. After he left, he would take several occasions to come back to Italy. Fatima, his wife, is Italian. I cannot hide the fact that the name of the two children are Italian. And during many years, he visited several different universities in Italy, cementing a community around category theory in Italy. And I shall look at few cases. He came to Italy
in 1972, he was there already in 69, we heard that, and in 71, Miles Thierry lectured on toposes, and the country was getting ready to learn category theory, even in these excerpts from the 9th volume of an opus of 11 on the history of scientific and philosophical thinking, edited by a philosopher, Ludovico Gemona, which appeared a few months before Bill came to Perugia. You can read, I translated that bit in English, that the research line for which certain experts shows more than any other this character of non-a priorism and of more direct contact with the scientific practice is given by the approach to logic and foundations of mathematics initiated with the works of F. William Lawvere around the mid-60s. It was 1972. The philosophers in Italy were learning already about category theory, about il programma di Lawvere, and in some 60 pages following that introduction, philosophers and anybody reading the volume would learn about the basics of category theory, Grothendieck toposes, elementary toposes. It's actually available now online. You can read it, and it's a short introduction to all these concepts. And they would learn already how to use diagrams, because this is a page from that chapter. Bill in Perugia taught a course on category theory over a base topos. The notes from that course have become known as the Perugia notes. He had several students attending that course, and I've listed some of those. I'm sure that all of you know some of those names, and some here know all of those names. They would become all researchers in category theory, possibly some of those just because they attended that course. In particular, there were 4 of them, Renato Betti, Aurelio Carboni, Massimo Galuzzi, and Giancarlo Meroni, who would travel from Milan to Perugia. I'm sure you have a picture of Italy like a boot. It's from the top of the boot to halfway through. Every week, 500 kilometers, not that difficult, but still, to attend the lectures of the course. That feat became legendary among mathematicians and researchers coming after them. They were known as the Gang of 4, la Banda dei Quattro, in reference to the Chinese original, and they were the 4 who translated in Italian in 1977 categories for the working mathematician. Unfortunately, the title, they were complaining about not managing the correct translation of the title, but that was the best they could get close to the English meaning. And they all gather inside Via Saldini 50. That's the way the Department of Mathematics of the University of Milan is known among the aficionados. In that department, in the journal published by that department, Bill would present the paper on metric spaces, generalized logic, and closed categories. The Gang of 4 would reside actually in a few offices in the cellar of the department. You would go there and you would immediately understand that it was a smoke room. That was allowed at that time. I know it would be inappropriate now, but that was the place where many of the Italian researchers enjoying talking about category theory know they had to do. The Department of Mathematics in Milan became the center of the category theoretical activities in Italy. Another example of Bill influence in Italy was in Florence with the Department of Philosophy. This is a picture of the conference, taken at the conference on ramifications of category theory in 2003. You can see Bill in the middle. And, well, the influence on that conference is already explained by the poster for the conference. I'm sure you recognize where those 4 pictures come from. And it was an incredibly interesting meeting of different schools. There were mathematicians, there were philosophers, and computer scientists. And they were all there because Bill wanted that to happen. Also, I would like to finish mentioning the award he received of the Giulio Preti Prize in 2010. He actually received it in April of 2011. This is the translation for the motivation. The prize goes to those who have distinguished themselves in a fruitful dialogue between science and philosophy, combining their own research activity in a given field of knowledge, both with a broad and innovative reflection on science, its history, and its philosophical meaning, and with a clear communicative ability, making it possible to reach a wide audience, thus promoting the junction between the values that guide scientific investigation and the values that inspire democracy. That's the way we usually speak in Italian. The sentence never finishes. But that's exactly what we've all been saying about Bill. And this is the final picture I have. It's taken during the Category Theory Conference in Genova in 2010. There is Bill, I'll let you spot it, who walks away in a group of category theorists. He's always been a champion of the subject, but he has always been able to surround himself of a lot of collaborators.
Grazie Pino, wonderful photographs. George, you're next.
My speech will include 7 sentences from MacLean's autobiography and 3 things Bill told me. First, from MacLean. From Eilenberg, he learned, he is Bill, some basic facts about categories and probably discovered for himself the central notion of an adjoint functor, a notion later formulated explicitly by Daniel Kahn while studying with Eilenberg in Columbia. You see, he probably discovered adjoint functors. And by the way, as you know, he made passages from adjoint functor to philosophy, all this discussion becoming, and he made passage to logic, and quantifiers are adjoints. And now I want to say one thing he told me. First, I told me that when I learned this, I was very happy to see that equality comes out exactly the same way as quantifiers. So if substitution functors between suitable Boolean algebras have both adjoints, for some special case you have quantifiers, for others you have equality. And Bill's answer was, yes, I was very happy to discover this. Next, from MacLean, Lawvere asked for truthful advice on which university to choose for graduate study, and was told, by all means, go work with Eilenberg. Trousdale was mentioned before today, but I want to add that he was a student of Solomon Lefschetz, and of course Steenrod was not far from that, and Eilenberg wrote a book of Steenrod, so it is all one company. Understandable why Trousdale suggested Eilenberg. Why did Bill ask for such advice? It is related to also what was said today. I think all physicists in the world are unhappy with sets because they always speak about differential equations, functions, and so on, but they do not want to consider functions as set theories do. But they simply ignore it. Bill, however, instead of ignoring it, wanted to justify it. And now is the second thing which he told me. He told me in, I think it was 89, that set theory was a historical mistake. No, Paul. I hope he changed his mind later. Anyway, I'm continuing from MacLean. One day, Semi, you all know who Semi is. By the way, Semi would turn 110 this year, so we should remember him. Semi told me he had a young student who claimed that he could do set theory without elements. It was hard to understand the idea, and he wondered if I could talk with the student. So Eilenberg wanted MacLean to talk to the student. Okay? Despite my belief in sets, I undertook to listen to Lawvere. I listened hard for over an hour. At the end, I said sadly, Bill, this just does not work. You cannot do sets without elements, sorry. And reported this result to Eilenberg. I skip a bit and continue from MacLean. When I sat down beside him, so what happens now is that Semi and Saunders are in the same plane, flying somehow. Him is Semi. When I sat down beside him, he turned to ask me if I remembered Lawvere and his dislike of four elements. And I did. Semi reached into his briefcase and pulled out a fat document to say, here is Lawvere's thesis. You are the reader. And he went promptly to sleep. MacLean didn't read it immediately. He had had some travels in between, but eventually he started to read it. And he continues. By the time I was halfway through, I was persuaded that there was indeed exciting material there. It included a foundation for mathematics based on axioms without elements for the category of sets and functions. In addition, there was a wholly new way of doing universal algebra. Neither Semi nor I had contemplated any such direction. Now, special reason why I wanted to read this is to say that yes, of course, eventually topos theory got its first beautiful shape in collaboration with Miles Tierney, and I'm sure that Miles Tierney had a beautiful contribution. He was very good, great admiration to him. But the whole point is that Lawvere wanted a new foundation of mathematics before anyone could even dream about this. And it is not the version of elementary topos which we know, but just axiomatizing sets. This was the big first step. And concerning a whole new way for universal algebra, I am coming to the third thing he told. I asked him, what about monads? Because the big point about Lawvere's theories against what universal algebraists were doing, that now we have algebraic theory without presentation. And this expression without presentation has very important meaning, because if we go back in history and look at the history of groups, groups were not seen for a long time as a set with operation. They were seen as presentation. You have several elements, you have several equalities between them, and whatever you deduce is good from these equalities. And only later. So, and the mathematical community at some point was very happy to get rid of this presentation and see a group as a set with operation. Now, second time the same is happening. We can see algebraic theory without presentation. So, if you see something second time, you should eventually learn it. But no, they didn't learn. And in '93, as you know, there was a conference, many of us were there, in Berkeley, joint universal algebra and category theory, where Fields medalist Thurston, who was director of Berkeley, he told us that, look, you are both bad, maybe at least you can talk to each other. And it was his opening speech, okay? And MacLean was, actually MacLean was most active to organize this. And MacLean's main idea, I know this because I talked to him about this, main idea was to explain what is Lawvere's theory to universal algebraists. There are many other things, but this was his main desire. It didn't happen. The only thing which did happen is that discussions were only in restaurants and only about the fact if algebra can be empty or not. We insisted it can be, they insisted it cannot be. And one more comment, if you allow me, related to this. There are two things logicians should have learned from Bill, and they didn't. I mean, there are many things, but these two are very, very simple to say. First, once you understand adjoint as quantifiers, you understand that Gödel completeness theorem is formulated badly, because it speaks of non-empty model. And once you understand adjoint as quantifier, there's no time to elaborate, I'm very happy to explain if anyone interested. Once you understand this, that in Gödel's theorem you can include empty model. Second thing is what I already mentioned. If you look at open any book in logic, you see that they don't know, do they want to speak about first order theories with equality or without equality. Now from Bill they can learn, yes, equality is as needed as quantifiers. Walter, should I stop?
I think we are coming to...
Okay, then last fragment, and this is something I don't understand well, so I want just to read MacLean. Lawvere was an assistant professor in Chicago when I taught a version of this course. And this course was everything, physics, gravitation, whatever. From listening to my use of differential geometry, he came to think about the justification of all the intuitive methods, Sophus Lee and others, in geometry. This in turn led him to start to develop the subject synthetic differential geometry, which was used a version of actual infinitesimals to formulate geometric ideas. His current student, Anders Kock, took up the idea, as did others, including my student Eduardo Dubois. There was a full-blown development of these ideas, which do indeed provide a working system of infinitesimals in geometry, as presented, for example, in a book by Moerdijk and Reyes, Ieke. However, those promising ideas have not yet entered into everyday use by differential geometers, unless you agree with me on this. All right, thank you very much.
Thank you, George. You got a little bit into my time for some concluding remarks, so please bear with me for another 2 or 3 minutes. When I thought about this whole thing, I asked myself, are there maybe 3 or 4 nouns that characterize Bill? And the only thing I could come up with immediately was vision. And I think we heard a lot about his mathematical vision. Passion. He was passionate not just about category theory, anything he did, political views, but also the cause of education, whatever comes to mind. And the third, I would say it's generosity. We heard how generous he was with his time for everybody, writing emails, speaking to you personally, etc. And if you allow me, I'll give you a sort of funny little anecdote. I have many things, because he used to call me often when he thought something is wrong in the world of category theory, whatever. But he is a very sort of funny thing, not deep at all. So in the 80s, when I was new at York, we had this really bad course. It was called set theory. And it was a course for undergraduates, and they usually had very bad students because it was not one of the required courses. They just picked it to get some extra credits. And everything that I knew about that course, I never thought that really turned me off. And then it just so happened that there landed on my desk mimeographed notes from the Buffalo Workshop Press called Conceptual Mathematics. And, oh, here is my way to manipulate that course. And so I asked the bookstore to have copies available to order from Buffalo Workshop Press. And one day, late afternoon, I leave my office and walk around campus as usual, and near the bookstore, and there was a car parked. I was in a bus, unfortunately, with public transport, but I see Bill and Fatima unloading boxes of conceptual mathematics. That is commitment. That is value time. That is believing in a cause. And I think that says a lot about Bill. And I want to show you maybe some of my own and mostly bad quality pictures. The first we have seen This is from YouTube. But here is that quality picture, 1999, Coimbra, McLean's 90th birthday celebration, and Bill celebrating the Jubilee. Of course, you see Max Kelly there also in the background.
I'm also there behind Max.
You have all your favorite gods in front of you. Just this is a candid shot. It's a bad picture, but I like it because it shows, Bill smiling, and together with Fatima, you will recognize several people in the background. And you heard a lot about topos theory. There's also a bad quality picture from the internet from the Union College meeting in 2013. But here you have the two creators of elementary topos theory. And I want to leave you with Bill speaking to us, because just a year earlier, another great mathematician of vision and passion passed away, Jean Benabou. And Bill, at that time, in August 2022, was already very, very sick. And but he felt the urge he had to say something about another great mathematician whom he obviously respected a lot. And he he dictated it to Fatima what he wanted to say, and Fatima eventually sent this to Francis Brosseux, who communicated this to me, and with her permission, I show you what Bill had to say. He obviously struggled to say something, but it just is another indicator how much he cared about category theory and the protagonists of category theory. And I leave you to read this, and the only thing I want to say, other than saying thank you to the presenters this afternoon, I want to say thank you to Bill.
Another person who obviously would be invited to sit with us and say about Bill would be Marta.
Yeah, thank you very much.